If you wanted a review of freshman chemistry and first semester organic, I hope you listened to part one of this video where I defined pH and I talked a little bit about how to work with logarithms and exponents, and I described the underlying idea of how buffers work. Now I want to go into this a little bit more rigorously and mathematically, and we're going to look at the Henderson-Hasselbalch equation. The pharmacist would like you to know this equation because a lot of pharmaceuticals are weak acids or weak bases, and how they are absorbed by your body and how they are transported through blood and get through membranes will depend upon the pH and upon the pKa of these weak acids and bases. Also, the physiologists want you to know this because we're talking about the buffering of blood and how that is controlled between the lungs and the kidneys and by human metabolism. Also, Henderson-Hasselbalch is based upon some broad-reaching chemical principles that may be even more important than Henderson-Hasselbalch itself. So, one of those principles is called the equilibrium constant of a chemical reaction. Let's say that you have an enzyme that takes A and B and converts it to C and D. No reaction goes to completion, meaning if you start with a whole bunch of AB and you expose it to the enzyme over a period of time till it reaches equilibrium, there will be some AB and some CD. If you start with pure CD and put it in an enzymatic reaction, it will form some A and B. But whether you started with only AB or only CD or only a mixture of both, regardless, at the end of the day, when equilibrium is reached, you will have the same amount of products over reactants, regardless of the starting conditions. And that's because it depends upon the relative chemical energy of products over reactants. And so in this reaction, that would be C times D over A times B. Will you write a chemical equilibrium constant for an acid dissociation reaction? That's where an acid dissociates into a proton and its conjugate base. Please go ahead and write that based upon what we just said. Now I'm going to move on. As an example, let's look at acetic acid. The products will be the acetate conjugate base and a proton, and the reactants will simply be acetic acid, the conjugate acid. So the Ka, the dissociation constant, will be the concentration of protons times the concentration of the conjugate base over the concentration of the conjugate acid. Now, will you define the pKa of an acid? Please do so, and you do know what it is. I'll give you a clue. What is pH? It's the same thing. Okay, let's look at that. So, of course, the pH is the negative log of the H, just as the pKa is the negative log of the Ka. And by using this same logarithmic function on both pH and pKa, it can somewhat simplify our working with them mathematically. Now, it also happens that the pKa of an acid is the same as the pH at which an acid is half protonated and half deprotonated. So in other words, if we took acetic acid, which has a pKa of 4.8, and we put it in a solution that's buffered at a pH of 4.8, what will be the ratio of conjugate base to conjugate acid? Well, we've just defined that. If the pH is equal to the pKa, then A minus will equal HA. In fact, you can see this in the Ka definition. If A minus equals HA, then A minus divided by HA is 1, and Ka equals H plus. Or, if Ka equals H plus, pKa equals pH. So you can see just from the equilibrium constant, the definition, pKa is equal to the pH at which an acid is half protonated. Now let's look again at acetic acid, and let's say that there's some of it in your blood. Can you tell me how you might get acetic acid in your blood or in your body to begin with? What might acetic acid be hydrolyzed off of? How about an acetyl group? For example, acetylcholine can be broken down to make acetic acid. So we have acetic acid in your blood. What will be the ratio of conjugate base to conjugate acid? Try to make an estimate. My first question is, if the pH were 4.8, what would be the ratio? 1 to 1, right? Now, the pH of blood is what? It's 7.4. So that's a higher pH. So will the ratio be greater than 1 to 1 for base to acid, or will it be less than 1 to 1 for base to acid? In other words, is there more base or more acid? Well, again, at 4.8, they're perfectly balanced. We've gone up 3 pH units. That means there's much higher pH, much fewer protons. If there's fewer protons, that means that you're going to be more in the conjugate base form. So think a lot about this, because this one simple rule you're going to apply to absolutely every problem you do with pH. At 4.8, we know they're 1 to 1. What do you think the difference would be if it's 5.8? Again, it's more basic, there's fewer protons, so you're going to have more of the base form. And it turns out these are logarithmic scales. So instead of 1 to 1, it's 10 to 1 base to acid. What do you want to guess it'll be at 6.8? Please guess. Another tenfold, it'll be 100 to 1. And at 7.8, 1,000 to 1. Now, 7.8 is not far from 7.4. And that's the type of thinking I want you to be able to do. I don't want you to go, oh, we better go between these pH logarithmic units. To me, to say it's 1,000 to 1, that's close enough. So, do you see the principle here? Anytime you have a problem where someone gives you the pKa and the pH, you can simply go, okay, we know that if the pKa equals the pH, that the conjugate base and acid are equal. Now we need to say, are we at a higher pH, in which case there's fewer protons, or are we a lower pH where there's a lot more protons, which will stick to the conjugate base and make more of the acid? Now, once you know the direction, then you can see how many pH units, and for each pH unit you move away from the pKa, there will be a tenfold difference in the ratio. Now, that is what I would call the poor man's Henderson-Hasselbalch. And if you do a few problems with this, it's going to make tests a lot easier. You don't have to formally go into Henderson-Hasselbalch. However, there might be problems which are more complicated and don't just involve being given the pKa and the pH, in which case you might need Henderson-Hasselbalch to solve it algebraically on a more complicated problem. So, we've been given these definitions of pKa, Ka, pH, and chemical equilibrium. Can you derive the Henderson-Hasselbalch equation, which says that the pH is equal to the pKa plus the log of A minus over HA? You can try to derive it. It's worth a little bit of a stab. But let me remind you of something again. What happens if A minus equals HA? Then you would have pH equals the pKa plus the log of 1. And what's the log of 1? 0. So the pH equals the pKa. That's such a fundamental and important definition that I want to make sure you remember it. But I'm going to go ahead and derive it, and simply I will remind you that we're looking at an acid dissociation reaction. So all we do is take the definition of an equilibrium constant, the equation that says Ka is equal to products over reactants. Now we want to solve for the pH, so let's solve for the proton concentration first. To get protons alone, we will divide both sides by A minus, multiply both sides by HA, and we get that the protons is equal to the Ka times HA over A minus. If that was too fast, play with it a little. Solve for H. There's multiple ways of doing it, and you can do a lot of steps, but we now have the protons alone. The next step, we're trying to find the pH, which is the negative log, so let's take the logarithm of both sides of the equation. The logarithm of the proton concentration is equal to the log of the Ka times HA over A. Now we can multiply both sides by -1. And I'm going to go another step here. And this is a principle of logarithms. Look, you don't have to do this, but you're welcome to come to me or I can make a video on this. But logarithms are kind of interesting that the product within a logarithm is equal to the sum of the logs. So that the log of Ka times HA over A minus is equal to the log of Ka plus the log of HA over A minus. So we separated the logs and we multiplied by -1. So the negative log of the H plus is the pH, the negative log of the Ka is the pKa, that fundamental definition. Now the same rule that says you can separate a product in a log to be the sum of the logs, you can do the same with, it's exactly the same thing with a quotient, that basically the negative log of HA over A minus is equal to the positive log of A minus over HA. Again, these logarithmic rules, you can come and talk with me about them, but the point is that we have the pH is equal to the pKa plus the log of conjugate base over conjugate acid. Now I want you to do one other thing with the Henderson-Hasselbalch equation. What if conjugate base equals conjugate acid? If pH equals pKa, then you can subtract pH from both sides and you'll get 0 is equal to the log of A minus over HA. How can you get 0 from a logarithm? Only if A minus equals HA, so that 0 equals the log of 1. The definition of a pKa is that it's the pH at which the conjugate base equals the conjugate acid.
Many pharmaceuticals have acidic groups or basic groups and therefore exist in equilibrium between an acid form and a conjugate base form. And the pKa of these drugs can affect their absorbance in the intestine and can affect how they're distributed throughout the blood. And a really good example is aspirin, where the pKa value is clinically relevant. Which form of aspirin is most soluble in neutral water? Which form of aspirin is most likely to precipitate? And is aspirin more likely to precipitate in the stomach at a pH of 1.5 or in the intestine at a pH of 7? Explain. Please pause and think about equilibrium and try to answer this question. This will be the most useful exercise in the pH videos. I'm going to move on, but it's in your own interest to try to answer all of these first and to answer them as I go along also. Let's just look at language I always want to interpret. Aspirin is called acetyl salicylic acid. Acetyl because there's an acetyl group. Salicylic is the overall compound. Ic acid because this is the acid form. Alternatively, when a positively charged proton comes off, you then have acetyl salicylate because 8 is the conjugate base. Which form is more soluble in neutral water? Well, if it's in neutral water, it is an acid. It is a proton donor, which means it will exist mostly as the conjugate base. And that conjugate base has a negative charge, and a negative charged compound is much more likely to be soluble than a neutral compound, especially when they have a big aromatic group on them. So the conjugate base being charged will certainly be more soluble than the conjugate acid form. Which form is most likely to precipitate? Well, that's really the same question, right? If the conjugate base is more soluble, then the conjugate acid is more likely to precipitate. And for that matter, think of this base trying to precipitate. One of them is negatively charged. Real unlikely a second will pack on top of it because they will repel each other. A third one would be even more charged, a fourth one even more. You just can't put all these negative charges together. So real unlikely for the conjugate base to precipitate. Is aspirin more likely to precipitate in the stomach or in the intestine? Please go ahead and answer. It's in your interest. But I'm going to move on. Well, in the stomach with a pH of 1.5, there are a lot more protons than there are in the intestine with a pH of 7, because pH and proton concentration are inversely related and it's logarithmic. So the stomach has a lot more protons than the intestine, and when there's a whole bunch more protons, they'll tend to stick to the conjugate base to form more of the conjugate acid. And since we said the conjugate acid is more likely to precipitate, precipitation in the stomach is more likely than in the intestine. Furthermore, how much more conjugate acid will there be than conjugate base in the stomach? What will the ratio be? To answer this question, you can memorize the Henderson-Hasselbalch equation and plug in values. But I see that as an exercise in memorizing gibberish, which you could forget at any time, and simply doing algebra, which anyone can do. I think it's actually easier, and you'll remember how to think about acids and base in pharmaceuticals better if you actually understand what the Henderson-Hasselbalch equation represents. To put this in context, the first thing I think you should do is set the pH equal to the pKa. Now, does that mean that we want to work with a pH and a pKa equal to 3.5 or a pH and pKa equal to 1.5? Well, you can only change one of the values. pKa is the dissociation constant of aspirin. That value cannot change, but aspirin can be put in a solution of just about any pH, so you can't change the 3.5 value. Easy to change the 1.5. And we're just going to say that we put this aspirin in a solution at a pH of 3.5. And at that we know that the value will be 1 to 1. Now, the next thing you ask is, in order to get into the stomach, is the pH going to go up or down? Well, the stomach is 1.5, so we're going from 3.5 down to 1.5. I've thrown in this extra step here of looking at the proton concentration rather than the pH because humans naturally think in terms of correlations rather than inverse correlations. So you just need to remember that when the pH goes down, the proton concentration goes up, which means there's more and more protons, you're going to tend to have more conjugate acid. Le Chatelier's principle. So let's look at that. We said that if the pH were 3.5 to match the pKa, there's a ratio of 1 to 1. What if it were 2.5? Please give me that ratio. Remember that if pH equals pKa, that means that H equals Ka. So if the protons equal the Ka, you could divide both sides by protons, you get 1 equals A minus over HA. If you add 10 times as many protons, the only way you can remain a constant value is if A minus over HA decreases tenfold. It's the only way you get a constant value. Not only do you have more conjugate acid, but you have exactly 10 times. What now if you go down to a pH of 1.5? That means that now you're another tenfold higher in protons. The only way to do that is if the conjugate base over conjugate acid is another tenfold lower, such that you will now have 1 to 100 conjugate base to conjugate acid. So that means that for every single conjugate base which is water soluble, you'll have 100 conjugate acid which have been protonated in our neutral and could precipitate. Now let's see what happens in the intestine, where instead of having an acidic environment, we have a relatively neutral environment. In fact, the pH varies throughout the length of the intestine and depending on time, but it's around 7, or we'll say 7.5. We do the exact same thing. We think what will happen if the pH equals the pKa. The Ka is a constant. It's an equilibrium constant for the acid. It'll never change. So we think of pH equal 3.5. What will the ratio of conjugate base to conjugate acid be? Well, it'll have to be 1 to 1, because for the pH to be equal to the pKa, the Ka will have to be equal to the proton concentration. Now we're going up in pH, which means there are fewer protons. At this point, I want you to remember that the proton concentration in the stomach or the intestine or the blood is not going to be affected by the aspirin itself. There's so little aspirin in comparison to all the other buffers and molecules which are in your body
that the proton concentration is driven by the body, not by the acid, but then in turn the protons will drive whether you get conjugate base or conjugate acid based on the pKa. So if we go up in pH from 3.5 to 4.5, that means the concentration of protons has decreased tenfold in our system. The only way for that to happen is if the conjugate base to conjugate acid increases tenfold. Then let's think if we go up to 5.5, there's another tenfold decrease in the amount of protons. The only way to maintain a constant equilibrium constant is for the additional tenfold decrease concentration in protons to correspond to another tenfold increase in the ratio of conjugate base to conjugate acid. And again, you think about it, we're in the intestine, it's more basic, there are fewer protons, not as many are going to be able to stick on the conjugate base to make the conjugate acid. We change another tenfold, what will happen? Well, now it's 1,000 to 1. Then we go up to 7.5, it's close to the pH of your blood, typical of the intestine. What do we have now for conjugate base to conjugate acid? You have another tenfold change, 10,000 to 1. So what this means is that if you take aspirin in your stomach, there's a real good chance it will precipitate. And a pile of aspirin sitting on the lining of your stomach can leak into the cells and damage them, leading to ulcers. But at the same time, we would like to have the soluble form of aspirin in your intestine where it can be absorbed, enter your blood, and travel throughout your body. So how do we do this? Well, we don't take the type of aspirin I was given as a child. We don't take the pure white aspirin tablets. Rather, they are coated with a carbohydrate which cannot be digested in your mouth and it cannot be digested in your stomach. But it can be digested by the digestive enzymes in your intestine. So therefore, harmlessly, this goes through the mouth, through the esophagus, through the stomach, into the intestine, where now the carbohydrate covering will be torn apart, the aspirin will be released, and it can then slowly get through the lining of the intestine into your blood and transported throughout your body. Now that's as far as I want to take the aspirin example. If you want, you can practice with another non-steroidal anti-inflammatory drug called naproxen. It's a little bit similar to aspirin. Its pKa is 4.2. So if you think about that, you could say, what is the ratio of conjugate base to conjugate acid in the stomach? And if you want in your blood at a pH of 7.4, you could set the stomach acid to 1.2 just to make the math easy. And you'll notice that these are weak acids. Acids are proton donors because the pKa, the equilibrium, is below physiological. If you put naproxen with this low pKa, this acidic pKa, into the blood at a pH of 7.4, there's not enough protons to stick to it, so you will tend to become the deprotonated conjugate base form. What's interesting is another compound that's quite a bit of it in your intestine is ammonia, and it exists in equilibrium between ammonia and ammonium. And I can write this as a conjugate base conjugate acid pair. This is called a weak base instead of a weak acid because its pKa is above physiological. How can you remember whether ammonium or ammonia is the deprotonated neutral form or is the protonated charged form? Please think for a minute. Don't think too much, but can you figure it out? Well, just think of normal nomenclature. What elements end with ium? You have sodium, potassium, calcium, magnesium. Do you have a clue? What does ium mean? Ium means positive charge, just like anion means negative charge. So when a neutral ammonia with its lone pair of electrons grabs a proton off of a water molecule, it becomes the positively charged ammonium. And if the proton comes back off to make the neutral ammonia, it's called ammonia. It helps to get that nomenclature straight without really memorizing gibberish or using mnemonics. Look at this as an acid dissociation, and use the same algorithm you used for the aspirin and for the naproxen, okay? And see if you can give me the conjugate base to conjugate acid ratio in the stomach at, say, a pH of about maybe 1.4, or in the blood at a pH of about 7.4. Those would be good exercises. I'll ask similar things on the quiz. Again, the quizzes are completely for your benefit, but boy, it's in your interest to try to answer those questions, and if you get them wrong, to figure out why. And again, I always welcome questions. I do recommend that now you're done with part 2 of the pH talk, that you do take the post-quiz. And also I recommend that you take the pre-quiz for the next section and move on with it. I'd like to hear from you, see how you're doing with this stuff. Thanks.